Hello everyone, my name is Yang Shu, one of the authors of this paper. Today I'm so happy to present our paper. The title is Learning Common Rationale to Improve Self-Surprised Representation for Fine-Grained Vision Cognition Problems. Fine-grained vision recognition aims to distinguish subcategories of objects under basic level classes, such as both specials, car models, or aircraft models. In covered work, self-supervised learning strategies may be less effective and have a coarse-grained bias in learning representations for fine-grained vision cognition, because many features helpful for optimizing self-supervised learning objectives are not suitable for characterizing the subtype differences in fine-grained vision cognition. So we propose learning an additional screening mechanism to identify discriminative clauses commonly seen across instances and classes. We can call this as common rationale. We aim to design a gray-can fitting branch which tends to characterize the discriminative patterns that commonly occur across samples due to its limited fitting capacity. And those common patterns we can call as common rationale in this work are more likely responding to the discriminative clause from the key object's parts or at least the free ground regions. Our overall framework is shown here, where the encoder in the framework represents Molecule-based contrastive learning is used to create the image level representation. We only add one gray-can fitting branch and fit the gray-can generated from the CL loss at the training time. At the testing time, we let this gray-can fitting branch predict gray-can and use the prediction as an attention mask to perform weighted average polling over the convolutional future map. We expect gray-can fitting branch has a limited filtering capability, so that the branch will not overfit the gray-can, but only capture the commonly occurring discriminative patterns, for example, common rationale. Our total loss function consists of contrastive learning loss and KL loss, where contrastive learning loss represent molecule-based contrastive learning. The model tries to minimize the distance between different views of the sample of the same images and push away the views of different images. In addition to contrastive learning loss, we require the gray-can fitting branch to produce a similar attention map as the one produced from the gray-can. KL loss means learning common rationale loss, where at the training time we use an additional branch with limited fitting capacity to fit the gray-can calculated from the self-supervised learning objective. We also compare the proposed method against commonly used self-supervised learning methods. We report the top 1 accuracy, the running time, and the p-memory with 2 different batch sizes. It is clear that our method achieves the best top 1 performance on the COB, Stanford car, and aircraft datasets. Also, when the GPU resources are limited, for example, only one V111 GPU is available, the proposed method reduces the batch size, but still remain a competitive classification performance compared to other self-supervised learning methods. Our method is featured by its capability of discovering the key discriminative regions, which is vital for fine-grained vision recognition problem. We compared the proposed method with 9 alternative solutions to take object localization into account. Compared with the other localization-aware self-supervised learning methods, our method shows a clear advantage, especially for the retrieval task. We also conduct some ablation studies to analyze the impact of a number of projections and alternative structure for Wickham fitting branch. In order to better analyze the importance of each projection, we consider the variance of the output of each projection. Higher variance indicates strong signal strength. It can be seen in imaging that projections with higher variance tend to produce more meaningful output. For example, a projection with the highest variance seems to capture clues that humans rely on to judge fine-grained objects. For example, the head, the body, or the back of the bird. In contrast, projections with the lowest variance barely attain the reasonable ranges. This is my paper presentation. Thanks for listening.